Okay, so I hope from the last video um, you have some a different way of observing the function when it has been asked to imagine that as a vector. Okay, and with that understanding we will discuss the Green's function. Okay, so from the last video you know that so discrete representation of a delta function is 0 everywhere except some place. Okay, except some place it's going to be 1. Okay, and that's our delta function. And let's say mainly what I need is ax is equal to b is what most of the time I need to solve. Okay, and so when we need to solve a differential equation, we will convert that differential equation into an operator like a, okay, and a column vector b, which will be the result when the a acts on x. Okay, um, in a finite dimension, what do? We just invert the a and we solve it. Okay, so instead what we could do is, we will just solve for I'll call that as, or maybe I could call xg, okay, which is equal to, I'll call that as a delta function. Okay, so maybe this entry is the kth entry. Okay, so I'll put k, okay, delta k. Okay, and this xg is the solution corresponding to delta k, so I will put k. Okay, so now this xgk is the discrete Green function. Okay, discrete Green function. And now for each k I am calculating what is xgk. Okay, but finally what I need to solve is, I need to solve for this equation. Now the idea is, for any b vector, any arbitrary b vector, okay, so the b vector, I can represent that as a linear combination of this del k. Okay, a linear combination of del k. Say c is not a vector, so okay, ck, or let me put k down, ck del k and summation. Okay, a linear combination of del k will give me b. Okay, now what am I going to do is the following. If this is the case, then in the place of b I could put ax, right, this equation. So ax is equal to summation of ck del k, right, where del is a vector. So let me put it like this. Even here let me put it like this. Okay, now what am I going to do is I'm going to use this equation. So let me take, okay, from this equation I can say that x gk, which is equal to A inverse del k, right? So let me take an inverse of A, so that I will get x delta, which is equal to summation of ck A inverse del k, right? And what is this thing? This thing is nothing but xgk. Okay, so I am going to write summation of ck xgk. Okay, so that's our solution for x. So here the thing is, so it may look like instead of solving a single equation, I have to solve, for example, if it has a dimension of n, I have to solve n dimension equations. So that's not at all efficient. But the thing is, once we have a set of Green's function, okay, once we have a set of Green's function for a, okay, that's corresponding to a, right, then the solution is nothing but a linear combination of that Green's function, isn't it? Okay, so this is what a discrete Green function represents, and we can do the same thing. Okay, we can implement the same idea in the function as well, and that's a continuous function as well, and that's what the Green's function, okay, where L is going to be a differential operator which acts on U, okay, provides me f, okay, so U of x, L of x, okay. For example, L could be d square by dx square, okay, so d square by dx square, or who knows, plus d by dx, it could also be like this, so which means d square by dx square plus d by dx, which acts on u of x, provide me f of x. Okay, now imagine this as a, okay, imagine this as the x vector, and imagine this as a b vector in the discussion we had over here. Okay, so that's the and for this we know the discrete function. What we will do is L into ug, instead of ug we will just directly put g for Green's function, okay, g of x, and in the place of k I will just put k or a, shall we put a, which is equal to delta of x minus a, and we will get all the solutions. Okay, so by all the solutions for different a we will have different g of x, that's what, okay, and then the solution is just going to be a linear combination of this g. Okay, so that's how we use Green's function. So I hope you understand geometrical way of thinking how the Green's function is operating. And one more thing, so this A is a linear operator which is acting on X. Okay, similarly, in order to have this Green's function work, this L has to be a linear operator. Okay, so that's one important fact we need to remember. Thank you.